magnitude comparator. Now magnitude comparator compares two given binary bits on three basic label. One would be equality, greater than, and smaller than. Okay, these are the three things, and we need three functions to implement each. Whenever one of them is true, obviously one of them is true, and that particular function goes as 1. Okay, not all of them are 1 at the simultaneous time, only one of them is high at the simultaneous time. Okay, so whenever that is true, that particular operation goes as high and other two remains as 0. Okay, so we have to design those functions. Now XNOR operation is used as equality operator. Okay, we call it that as an equality operator. This is XNOR. Okay, why equality operator? Because whenever the two inputs are equal, your output goes high, and that's the reason we call it equality operator or XNOR. So we can use XNOR operator to find the equality. Suppose we are given with 4-bit, two 4-bit binary bits. What we do is we calculate this particular function, that is the respective XNOR operation. X0 would be A0 XNOR B0. Okay, X1 would be A1 XNOR B1, and as such. And that will give us the final number, final binary number. And what we do is we add all the bits together. So what happens is, if all the bits are same, then all the x of I are going to be high, and the AND operation would be also high. So x of I would be high. That will represent us that all the bits are equal. If any of them is unequal, then one of the x of I would be 0, and that will make the whole expression x of I is equal to 0. So that will show us that none of the bits are, at least one of them is unequal. That will indirectly signify that the two numbers are not equal. So equality goes out of the way. Okay. So what we do is, after that we go for greater than or smaller than comparison. Now we take the help of this x of I here. X of 3, x of 2, x of 1, and x of 0. We take the help of these four expressions, that is XOR operations. For this particular case, that is 4 XOR, but that can increase if we have a larger number of for comparison. Okay, so it has a general structure of this. If you go for this, like for greater than, what we have is we begin with the most significant bit, that is A3, B3 complement, the second number complement, plus we start with X3, A2, B2 complement. We again go for like X3, X2, there is an addition of XNOR operation here. So the structure remains the very same. By looking at the structure, you can calculate what should be the expression of any number that is greater than this AI on and B of I. Okay, you see A3 B3 the second number complement, A2 B2 the second number complement again, A1 B1 the second number complement, B1 complement, A0 B0 the second number complement, and that's only for greater than. A is greater than B, whereas for A smaller than B we have the reverse of that. Okay, we have the reverse of that. If we have a fifth bit, then the expression would be a 5-bit expression, like A4 B4 complement. Okay, as we have 4 bits, we have the expression is 4-bit long. By looking at the expression, you can deduce that what should be the general structure for this expression calculation. I can go into the details of this, but that is not necessary, because with this structural difference, you can easily calculate what should be the expression of any higher number bit comparison. Okay. Now you can implement that very thing with logic diagram, and that will give us the 3 expressions here. Okay, only one of them would be high at a single time, whereas other two would be 0, and whichever is high, that particular statement is true. Okay, so this is how you design a comparator, magnitude comparator.